we have this conductor, length 2A, so A from there, A to there, and there's the field point that we're interested in. The magnetic field is going into the page there, and the length between the origin here to a little piece of the length of here, which we're calling DL, this length from there to the DL section is Y, and the length from O to the point is X. And obviously we're going to call this distance from the actual small piece of the conductor DL, we're going to call that length R. So the geometry is reminiscent of the electric field problem, where we found the electric field caused by a line of charge of length 2A. Although the shapes of the sources are the same in these two problems, the behaviour of the magnetic field is completely different from the electric field. We begin by identifying an element of the conductor having length dl. We'll call that dy. It's a little bit of the length here, so we'll name that dy. And we'll use this equation here as we worked out. That's the equation for the magnetic field, which was equivalent to the Coulomb's law that we showed before. So we're going to use this equation now. We can also use the fact that the ratio sine theta is the same value as the ratio sine pi minus theta. So you can see here that if we have this angle all the way around is obviously pi, this angle here is pi minus this angle theta. Okay, because the direction of the unit vector r is pointing down here, and we're going in this direction up here. We're saying that the current is moving in this direction here. Then the angle between them is theta. But because we've got these values here, it's much nicer if we can work with that angle. Well, the fact is that if you look at the diagram of sine, you know, that's the sine of the angle there. There's the sine of the angle. You'll see that theta, if you just go all the way around pi, then pi minus theta, the length of the sine is exactly the same as theta. So then we can just say that sine of theta is exactly the same. It's going to give you exactly the same number as sine pi minus theta. You can prove that with a calculator. For example, if you do sine 45, and then you type sine 180 minus 45, you'll find that they both come to something like 0.707 something or other. So you can check that on your calculator. So with that, we can then use that for this part of the equation here. The other thing we know is that now that we're using this angle, this makes things a lot easier, because we know that r is the square root of x squared plus y squared, using Pythag, and also that sine pi minus theta is x over x squared plus y squared. So we've got those associations there. We've got sine pi minus alpha equals x over x squared plus y. So that's sine is the opposite divided by the hypotenuse, so that's x over, remember we said r is the square root of x squared plus y squared, so that's where that comes from. So we can use these now to insert into this equation, which makes everything easier. So the direction of the magnetic field B is perpendicular to the plane of the figure. As I said, that the magnetic figure is going into the plane. In this case, the direction of the dBs from all elements of the conductor are the same. Thus, in integrating over the conductor, we can just add their magnitudes. If we put all these pieces together, we can bring out the constants here, and then what we've done now is we replace the dl with dy here, and we've done all the substitutions into here, and we end up with this. Now, of course, we want to integrate from here to here. So that gives us our integration limit, our limits of integration. So that's what we've set up. We've set this up now to find the magnitude. So the little bit of dB now gives us the full magnetic field here will be when we calculate all the little parts of 2A all the way along this conductor here. So that's why we can let that be B. Okay. In fact, we did this before. It was quite a complicated integral in one of my other videos. But for this example, that's just plug that into Wolfram Alpha, or just accept that the integral of that is this. So we end up with, once we've integrated that from a to minus a, we end up with the magnitude of the magnetic field B is equal to this equation here. An alternative route to this equation, Biot and Savart equations here, we can use these, and with the appropriate vectors we have dl, so we can have the fact that dl equals dy j, so the dl part is like the j component, so where j is the usual unit vector in the y direction. Also r hat, the unit vector r hat, is basically xi minus yj, that's for this line here, and of course to get the unit vector r, then we simply do the square, it's over the magnitude of r, so the unit vector is xi minus yi over the magnitude of this length here, which is square root of x squared plus y squared. So then we've got the unit vector here. So okay, I've got it, dl equals dyj, and I've written down here, let's just put those in boxes so you can see them clearly. So this is the alternative way of doing it, by using vectors. So we've got dl equals dyj, and then we've got the unit vector r. So with these, and using these two equations, then we can just substitute those values in. So we've got dyj crossed with xi minus yj over this. Now, if you work out the cross product of that using, you can use the matrix determinant. I've shown you in the video about cross products. You can simply do that, and then you end up with minus kx. So you can see from using the cross product, you end up with this same equation here, more or less, except now we've got the direction that the resultant B vector is pointing in. So that's quite good. So by using the vector way of doing this, it actually gives us straight away the direction. So if we use the standard conventional right hand coordinate systems, which we always do, then you'll find by treating this as vectors, you'll get the direction of the magnetic field vector. At points in the xy plane to the left of the y-axis, of course, the direction of the B is opposite and out of the plane. So if we're over here, then we're coming out of the plane. That's going in. Now on this side, it's coming up, yeah? Because remember, it's like it's going round. You put your thumb in the direction of the current, and you can see, like, and then when you come out the other side, you're going like this. Okay, let's consider the situation when this length here is very, very long. In other words, the 2a length is very long compared to its distance 0 to the point P. Given that, so we're saying when a here is much, much larger than x, then the square root of x squared plus a squared just reduces to a. So that becomes a, but you can see there's an a at the top there, so they cancel. So you just end up with ui2 minus k over 4 pi x, which is what we've got here. Okay, so that's how we get that. Now, because the physical situation has axial symmetry about the y-axis, B has same magnitude at all points on a circle centered on the conductor. If we imagine a circle going round here like so, a circle going round, then the B vector is like this, going around the circle like so, and that's how it will look. That's at all points on the circle. So all points on the circle around the of radius r around the conductor, the magnitude is given by that. So at all points on this circle, the size of the magnetic field vector is given by this equation here. Okay, so for every r we can just get this value for a long straight wire.